So last time we sort of wrapped up chapter one. I mean, the last part I did quickly because you were going to do that in the lab, really. So the simulation part I left completely for the lab. So did you go through you tried to, did Moeen introduce PSpice and you were able to run some of the circuits that are maybe at the end, the simple circuit at the end of the chapter? Okay, that's good. So I also posted homework one. It will not be due next week. I gave it a little bit more time and I included some problems from chapter two. Okay, so I think I gave it 2 weeks, and we'll include some problems from chapter two. So that's posted up here already. And on the due date, I will hopefully let's put the solution for the homework. Okay. So it's a few problems from the textbook, guys. The homework is for you to learn, right? So it's from the textbook, so I am sure 100% if you Google search and you spend enough time, you will find the solution manual, right? So everything is out there, but it's for your sake, okay? I mean, you use the equation sheet, learn how to use it, solve the problems by yourself. I think that's, I mean, if you want me to put 0% on the homework and you do that, I prefer to do that, right? So it's a, I mean, you need to, I mean, your hand needs to move with the equations, right? So if you do that, then you will do well on the exams. It should not be a problem. So, okay, so moving on to chapter two. Chapter two is a review basically of what you've done before. So it's the equations for power, RMS, average value. So that the whole chapter is that. So it's stuff that is a bit boring, nothing new, but it's stuff that will be very useful. So if you want to calculate power loss in a device, you need to understand how to calculate power loss, energy switching energy, RMS values of waveforms, maximum values, peak, RMS versus peak, RMS for a sinusoidal waveform versus for a non-sinusoidal waveform, power in a sinusoidal environment versus non-sinusoidal environment. Remember, we are doing power conditioning, right? So we are chopping up voltages and currents, right? You saw what we were doing to the voltage, right? We were chopping it up to create something, right? You can chop it up to create a DC value, or you can chop it up to create an AC value of a different quantity, right? So we have a lot of non-sinusoidal waveforms as well as sinusoidal waveforms. Power or the meaning or definition of power in this case versus that case is a bit different. Not very different, but it's a bit different, and you have to understand the difference. Yeah. So that's the goal of this chapter. Just a review of some of the basic power calculation equations. So instantaneous power, we know, is just nothing but the multiplication of instantaneous voltage by instantaneous current. So this is an instantaneous voltage waveform, and this is some sort of instantaneous current waveform. Multiplying them by each other instantaneously will result in the instantaneous power waveform that you see down here, right? So that's that. How about this? Passive sign convention is an interesting, it's just something we want to agree on, okay? So especially when you go back to chapter one, the last thing we did in the chapter where we had this example circuit where they had some voltage polarities and current polarities, etc. on there, and then you wanted to see which switch to put in there, right? They had some polarities for voltage and current, right? These polarities, where did they come up with? Why can't we just flip the polarity, for example? And then you're not blocking positive voltage, you're blocking negative voltage. Where did they come up with these polarities? They came up with them from an agreement that we will all use throughout this chapter. And I mean, you used it probably in 214. You're just maybe it was not introduced officially as okay. Let's agree on this going forward. So going forward, we will agree that if you have a source, typically current will be coming out of a source, right? And voltage polarity on the source will be in this direction. So current will be coming out of the positive terminal or the positive polarity on the voltage source, on a source, current or voltage source. This will be the convention that we will use. Current will be coming out of the source. How about a load? Anything that's not a source. Anything that's not a source, in this case, positive power will be this voltage multiplied by this current in this direction. If the current was coming into the source, it would be an indication of what? Negative power, right? Power will be negative. The value of power, P equals V times I, will be negative if this current is flipped. right? Because this is the convention that we used here. For positive current, we use current coming out. For a load, we use the opposite convention for current flow, right? So for a load, we will assume the same voltage polarity, for example, but current will be coming into the positive terminal, and that will be the positive current sort of notation that we will utilize. So if current is coming out of a load, then that power is negative. So this V times I in that case for that load is negative. What does that mean? That means that the load is not consuming or absorbing power, it is actually generating power. So, and this is the case, for example, with sometimes you have machines, electric machines you have in a power system, or nicer, a better example, maybe hybrid vehicles, right? When the vehicle is braking, you can use that brake. You can do something called regenerative braking. So it's electrical braking instead of mechanical braking with pads. You do what is called regenerative braking. In regenerative braking, the motor is acting as a generator. So and it's feeding power. So it's feeding power into the batteries, right? So in that case, what is the motor doing? The motor was the load, right? It was consuming power. Current was coming into the motor, right? And now, and batteries were doing what? Batteries were providing power to the motor, so that was the positive power, right? Now the motor is acting as a generator during the regenerative braking period, and it's current. The polarity of current, assuming it's a DC motor, for example, for simplicity, then the polarity of the current was flipped, right? In AC, it will be a phase shift, but for simplicity, let's talk about DC. Then the current polarity out of a DC machine will be flipped. It's now a generating machine, a generator instead of a motor, and the battery is consuming power to recharge, right? So that's what we mean by the passive sign notation, right? So a switch is not a generator, it's not a source. So a switch would follow this sign notation, right? So we would, current would be coming into the positive terminal. If you go back to the slides in chapter 1, this last slide that we were talking about, you will see that here. So current will be coming into the positive terminal. Current will be coming into the positive terminal, right? So we stuck to the passive sign notation. If I flip these around, then I'm not using the passive sign notation anymore. Then I'm not treating this as not a source. It's at the end of the day, the switch is going to consume power, right? Power consumption in the switch will be the positive power consumption, right? So everybody's okay on this passive sign convention? So this is just an agreement between us, right? So we will agree to use this. It makes comments. It makes sense, and this is what you've been doing before, but I just want to stress it here. Okay? And in the power systems course, we'll do the same thing, because in the power systems course, there's a lot of capacitors that we install in the power system, and these capacitors, what they do is generate reactive power and pump it into the system. So it will become even more important when we talk about this in power systems. Yeah. Okay, energy. Again, I'm sorry for the boring equations, but in review. But energy is basically the integration of the instantaneous power, right? So, if you have an instantaneous power curve, and this is typically what you'll have for switching losses, right? You will have switching loss curve. You have losses that turn on and losses that turn off, and then conduction. So the switch is turning on, and then it's conducting, and then it's turning off. Remember what's happening in all these things? There's transitions between voltage and current. Voltage and current transitions. These voltage and current transitions, if the switch is turning off, it had high current, it had current, and then it's turning off, for example. This is turning on. So it had no current initially. So this is the current waveform, for example, and the green would be the voltage waveform. So it had no current, then you turn the switch on, current is flowing through, and then you turn it off, it has no current. Voltage does the opposite, right? If it's off, if the switch is off, it's blocking voltage. Then it's on, it's conducting. Does it have a voltage across it when it's conducting? Ideal switch doesn't, but in real switch does, because there's an RDS on for the MOSFET, right? So I squared times R is a voltage across the MOSFET. or there's a VCE across a BJT device, right? So there's a small voltage actually here, a small value of voltage, right? So there's small value of voltage, and the current is flowing through the switch because the switch is on in this case. And then you turn the switch off, it blocks positive voltage, and current goes down to 0. During the transitions, we said that currents and voltages overlap. There's a period of overlap, and that's why if this is V and this is I of t, the instantaneous power waveform will look like this, right? The switch when the switch is on, there is a small power loss that's called what? Conduction loss. Conduction loss due to what? Due to the fact that when there's current flowing, and the fact that if I'm using a MOSFET, I have a resistance in the path, right? This MOSFET has some resistance. The resistance to the MOSFET is RDS on. The voltage across the MOSFET, VDS, is I squared, this ID squared times RDS on. That's the voltage across the MOSFET. And that multiplied by the current, the voltage multiplied by the current, is the cause of this conduction power loss when the device is on. Okay? And then, when the device is turning on here, there is a transition between voltage and current where they are overlapping. They're both on. I mean, there's current and voltage in the device. Voltage is decreasing, current is ramping up, because devices have rise times and fall times. So if we go back to our data sheet, I don't know if I did that to show it you before, but for example, this is the MOSFET data sheet. You will see that where's time? Here. TR, rise time, and TF, fall time. There's fall time, and then there's rise time. So the devices need time. Again, it's very small, 65 nanoseconds for a MOSFET, for a low voltage MOSFET. Go and now search for a 6,000 volt IGBT and compare the rise times and fall times with this MOSFET that we're going to be using. You will find there it may be in hundreds of microseconds, right? Maybe 300-400 microseconds, or maybe up to a millisecond. I don't know. Probably microsecond, probably hundreds of microseconds. This is in nanoseconds, right? The IGBT, I know a 1200 volt IGBT, I remember off the top of my head, it was maybe 100 microseconds for a 1200 volt IGBT. Maybe for a 6000 volt IGBT, it would be higher. It will be higher, not maybe, it will be higher. But how much? I don't have a number at the top of my head. So but it would be good for you to go and search for that. So we showed the simple waveforms for the voltage and current across the switch, and that's, this is the reason why we need to understand, the equations for power and power loss, because we will have voltage and current waveforms. We can draw power loss, instantaneous power curves, and if I tell you what's the average power loss through a device, you will go, this is a switching period, for example. The device is, let's say this is switching period, starts from here, and then it repeats, right? So there's a turn off, the turn on conduction and turn off cycle. And then what's going to happen? It's going to repeat, right? So during a period, you will have the instantaneous power waveform. You can calculate the average power loss in the device. How would you calculate average power? Actually, how would you calculate switching energy? Switching energy would be what? Turn on energy loss, for example. If this is the turn on power, right? We said this is the turn on event, right, of the device. The voltage is dropping, current is rising, right? So this is the turn on, transition of the device. So how would I calculate the turn on energy loss? Energy. Exactly. So the area under the power curve is the energy loss. So for this period of time, then it's the turn on energy loss. If I take this period of time, it's a turn off energy loss. If I take the whole switching period, it's the power loss in the whole device, energy loss in the device. Okay. So how would you do that? We said the area under the curve is basically the integration of curve, right? So it's the energy is integration of instantaneous power, right? So you will be given such waveforms, for example, and be able to calculate. So simple waveforms like the one we saw here are an example, or more realistic waveforms like switching loss waveforms are the same. They're exactly the same. At the end of the day, you have a V and I, multiply them by each other. You can calculate whatever you want. Energy during a period of time, energy for the full switching cycle. And then if you have energy, so this is energy, integration of power during a period of time. And then if you want, it's from energy if you want to calculate power. Back to power, because you average power. If you want to calculate average power, you would do what? Average power is 1 over the period integrator. Actually, average value of any waveform is 1 over the period of any periodic waveform. Sorry, any periodic waveform is 1 over the period integration of that specific waveform over the period. Right? So if we've calculated energy already, like we did from the switching loss, and typically that's what you would do in the switching loss calculation, because typically you will have the voltage and current waveforms, and then the easiest thing for you to do is multiply these two by each other, calculate the instantaneous power. After you calculate the instantaneous power, if you could calculate the energy or the integration of that waveform, you will get the energy, switching energy loss. If you're talking about only a switching energy loss in these areas, or the energy lost in the switch during the whole switching cycle, which is from here, T1, from T1 all the way to T2. This would be your period, for example, right? If you have your energy and you would like to calculate power loss in the switch, how would you do that? If you have energy, which is W, we said that average power loss. If you would like now to calculate average power loss, how would you do that? You know that energy is the integration of the power. So average power is 1 over the period integration of power over the period, 0 to T or T1 to T2, right? So you take your whatever loss energy that you've calculated and divide it by the period, by a switching period, right? This would be the switching period in this case. Okay? I know it's boring and simple, but we have to go through it. They give some more examples in the text. You've done stuff like this before, so it's the same example that the same waveforms for voltage and current, and then they calculate energy, which is what we want to do first, typically, by just integrating the power curve. So from 0 to 6 milliseconds, we have 400 watts. From 6 milliseconds to 10 milliseconds, they have minus 300 watts. And then from 10 to 20 milliseconds, that's 0, right? Again, that's the switching period in this case, because the waveform repeats every 20 milliseconds. And our switching cycles are the same. They will be repeating, right? I will be switching, I create the on time, off time, on time, off time. So, and I have the on time and off time together is my switching period, right? Or my period in this case. Okay, so they calculated energy, which in this case is in joules, if the voltage and current are in volts and amps, right? And then they do the same thing. They want to calculate power loss. You can either do the integration, the full integration again, or since you know your energy, divide it by your period, and you get the same 60 watts instead of going through the full integration. Okay, so definition of DC power is V times I. So again, DC power is average power, right? So the reason we're stressing about this is because again, all our waveforms are not going to be nice fixed DC waveforms. They're all going to be these switching waveforms. So you have to understand that these switching waveforms have both an AC content and a DC content. Right? All of these switching waveforms, they will have AC content and DC content. And the AC content is the average value. So the DC content, sorry, is the average value. And the AC content is everything else besides the average value. Right? So DC power in this case, if you have, again, DC power is average power, so it's 1 over the period integration of V instantaneous power over the period. And if you happen to have a pure DC source, let's say you have a battery that's supplying a power electronic circuit, right? The battery voltage is DC, but the current you're drawing out of it is pulsed, for example. So in this case, you can take the DC voltage out and do the integration over just for the current, right? and do the same thing that was done in the previous example where they divided it up into sections and calculated the average value of that current. And it can be the opposite, right? You can have, there are circuits where we have very nice smooth DC current, but the voltage is a switch type of voltage, right? So there are certain families of converters called current source converters, where instead of chopping up voltage to create a different level of voltage, a value of voltage, you actually have a fixed DC current coming in, and you chop up the voltage to create another value of current, right? So it's you're controlling current instead of controlling voltage. So we will discuss that briefly as well later. But anyway, sometimes you can take the DC voltage out because it's a nice pure DC voltage, and the current is not pure DC, and you have to do the integration. Or it can be the opposite. Sometimes the current can come out of the integration, and the voltage has to stay inside for you to calculate the average power, right? So it's so another example. So you have a waveform. You have a circuit similar to this. You have a current source here that's pushing current into an inductor, and we have the corresponding waveforms here for current and voltage and instantaneous power. So just by looking at the waveforms, what is the value of average power? Right? The value of average power is 0, right? So because, again, you would have to do the integration of the instantaneous power over the full period, right? And if this area is equal to this area, and that's what it looks like because this is 20, this is minus 20, and this is fixed 4 amp peak, then because these two areas are the same, then the average value is 0. And that it makes sense because we know that do inductors and capacitors consume energy? Ideal inductors and capacitors. They don't. Ideal inductors and capacitors, they store energy for you to use it sometime, another time, right? So you charge a capacitor, right? And then you utilize that charge in a circuit, right? You charge an inductor. How do you charge an inductor? If you apply voltage, you build up a magnetic field. So the energy is stored actually in the magnetic field around the inductor. Capacitor, you store the energy in the charges across the on the charge across on the two plates that are separated by the dielectric, right? So this is energy in the inductor review. So we know that energy in the inductor is equal to half Li squared. That's something you've studied before. I want to go through the discussion and make sure that it's clear to everybody that average inductor voltage is 0 and then average capacitor current is 0. So all the waveforms we're going to be using in power electronics are going to be periodic waveforms. So we will only utilize periodic waveforms throughout the course. So for example, it's very typical that inductor current waveform will look something like this. And for capacitor voltage waveforms to look something like same, for example. Yeah, same as this, for example, right? And this is my switching period. This would be my switching period TS, right? So this would be my period. And my waveform would be repeating periodically. So the value of current at the beginning of the period, so I of T0 and I of T0 plus capital T or TS are equal. Do we agree? So this is always, we will only do steady state analysis. Of course, at the beginning a power converter is not, for example, the capacitor is not charged and the inductor is not charged. So capacitor voltage will actually rise. Inductor current will actually rise, right? But then at some point it will reach a steady state value. Right? So during this course, we will be mainly looking at steady-state analysis of power converters. Okay? So during steady-state conditions of a power electronic converter circuit, all waveforms are periodic. All waveforms are periodic. Voltage waveforms across a capacitor, current waveform through a capacitor, voltage and current waveform across and through an inductor, they're all periodic. So they will all follow something similar to this. And same thing with capacitor voltage, right? So capacitor voltage at T equals 0 will equal capacitor voltage at T equals 0 plus capital T, which is the end of the period, right? So if that's the case, then, and we agree on that, then we can write down these equations for, you know, inductor. I mean, the current through an inductor, for example, at t plus capital T is equal to that current at t, which is T0 that we were talking about, and the same thing with the voltage. The voltage and current will be periodic waveforms, right? So we know that the equation for an inductor is what? The equation for inductor voltage is VL is equal to L di by dt, correct? That's the voltage across an inductor equation. So the inductor current will equal what? IL of t is equal to 1 over L, right? Integration of VL of t dt plus IL of t0, correct? And this is t next step, right? So I can say this is t0 plus capital T, for example, right? This is one sampling period later, right? What do I know about this and this? Let me rewrite it. IL of t0 plus capital T is equal to 1 over L integration of VL of t dt plus IL of t0. So what do I know about this and this? This is IL of t0, and this is IL of t0 plus t. They're the same, right? So if I bring this from the right-hand side to the left-hand side, I will have this equation equal to 0, right? So 1 over L integration of VL of t dt is equal to 0, right? And if I multiply that by L over t, multiply both sides by L over t, then I'm left with 0 is equal to 1 over t integration of VL of t dt, right? So what is this? 1 over the period integration of a waveform over the period is what? It's average value. It's average value of a waveform, right? So this is the average value of inductor voltage, right? 1 over t integration of VL of t dt is the average value of inductor voltage, right? So we know that average value of inductor voltage is equal to 0. What does that mean? So this what we just talked about is written here, right? And it says that the average value of inductor voltage is equal to 0, which means that the inductor will not consume average power, right? Because the average power is equal to the average voltage multiplied by the average current. So since the average voltage across an inductor is equal to 0, then the average power is equal to 0, and it confirms what you know before, that an ideal inductor does not consume power. There is like instantaneous power, right? Is there instantaneous power being delivered from the source to the inductor or not? Yes, there is instantaneous, but there is power. I mean, there is power going from the source to the inductor. But what happens is the inductor is actually giving that energy back to the source during this part of the cycle. Okay? So there's an exchange of energy between the source and the load and vice versa. Right? So they're giving power is going back and forth. But there's no average power being consumed. Right? So the battery, or if this was a battery, for example, it will never die out. So even there's current, right? It will never die out. But of course, this is not realistic, right? Is this a realistic circuit? It's not. I mean, any circuit will have some resistance, right? Any wire will have resistance. Any inductor is made of wire. That wire will have resistance, so it will consume power. So at some point, the energy will be dissipated, and all the energy will be dissipated in the resistor. If you have a finite energy source, assume you have a finite energy source. So this also means that inductors look like what to a short circuit, to a DC? Short circuit, right? Sorry. So that also confirms what you know about, okay, in DC circuits, I put inductors as short circuits. In DC circuits, you put capacitors as open circuits, right? So that will confirm that, we will do that by confirming that average capacitor voltage is equal to, average capacitor current is equal to 0. Meaning if you have a DC current, which is the average value of current, trying to flow through a capacitor, it's going to behave like an open circuit, right? So That's the next slide. And the proof is the same. So the capacitor voltage and waveforms in steady state operating power converters is periodic. So voltage at the beginning of the period is equal to voltage at the end of the period. And the capacitor equation for capacitor current is IC equals C dVc by dt. So if you want to calculate voltage, you will integrate the current, 1 over C integration of the current. And you have to add your initial conditions. These two we know are the same because we said for periodic waveforms, Vc of V of t0 plus t is equal to V of t0. So you do the same thing, subtract them, equal to 0. Because they're equal to 0 and you can multiply by C over t on both sides, then you get 1 over t equals to integration of IC, the average value of current is equal to 1 over t, integration of the capacitor current over time, over the period, is equal to 0, which confirms two things, that the average capacitor current is 0. So if you put a capacitor in a DC circuit, you just put it as an open circuit. And it also confirms the fact that if you have a circuit with an ideal capacitor, there's no power consumption in the capacitor. Capacitors will store the energy. Yes, they will, and that's why we will use them. But there's no power consumption in an ideal capacitor. Real capacitors are not. Real capacitors are modeled as an ideal capacitor in series with a resistor. That's a simple model. So they will consume, obviously, because these capacitors are made of conducting materials, right? You have to charge a capacitor, so current has to flow onto the plates. The plates, the current flow path, etc., all of that has resistance. So there will be a loss, right? And the dielectric that is insulating the two plates, there is a dielectric strength and dielectric resistance. Fine, it's very high, but there is a resistance there, and then there is leakage current as well, right? So there is an equivalent circuit for a real capacitor, and of course the ideal capacitor that you know about. This is relevant for the ideal capacitor only. Okay, so again, the rest of the slides are just exercises, just simple exercises on waveforms and voltages and currents and calculations of power. The whole chapter is about how to calculate power, right? So this is an example of a simple circuit. So here what I have is I'm applying this pulse train to the base of this device. So what's going to happen when the device is, if the pulse is high, the device will be on. When the device is on, what's going on? Yeah, current will go from my supply, my VCC, my source, through my inductor, to the device, to the ground, and I've closed my loop, right? So I have to close, every circuit has to have a closed loop, right? So this is my source. My source has a positive terminal and negative terminal. Negative terminal has to is the ground terminal in this case. So I've closed the loop around this circuit, right? When the device is on. How about when the device is off? When the device is off, this doesn't exist. So there's no connection between the source and its negative terminal, right? There's no closed loop between the source and the circuit, right? This is open, right? It's an open circuit. But I know that the inductor was charged. There is energy stored in the inductor, right? Half Li squared. It's there. There is energy stored in the inductor. And where will it go? If I did not have an alternative path for it to go, and I open the switch, it will just arc across the switch, and the energy will be dissipated in this arc. That's inductor energy will be dissipated in that arc. After the arc energy is dissipated, that's it. The switch will open, right? Theoretically speaking, if it doesn't burn down, right? But in power electronics, we don't do that again. So we create a bypass circuit, or a freewheeling circuit is what we call it in power electronics terms, for the current to flow. So the inductor current will never change directions instantaneously. So it was flowing this way, it will keep flowing this way until it's dissipated, right? It goes down to 0, right? So where will it flow? We put a diode here. How does the diode turn on? If it sees forward current, right? If you're pushing forward current to the diode, it will turn on. So the current will flow through this freewheeling circuit here, right? It will never be going back to the supply, because for it to go back to the supply, it has to go back through its negative terminal as well, right? There has to be a closed loop, right? So there is no closed loop between the supply and ground here at all, because this is an open circuit. So it will just flow through here, and the energy in the inductor will be dissipated in the resistor. So you've done things like this before in 214. What will the current waveform look like? So let's look at both cases. So in this case, when the switch is on, what will the current in the inductor look like? I'm applying a DC voltage across the inductor, right? Do we agree? I applied VCC across the inductor to ground, right? That's all I did here. So let me draw the waveform. And so I applied VCC across the inductor during from 0 to T1. What will the current look like? VL is equal to L di by dt. I is equal to 1 over L integration of VL dt, correct? So what does it look like? What does the current look like? No, not 0. VL, what's VL? Yeah, VL is this VCC. So I'm integrating, what's the integration of a constant? No, it's a ramp, right? Integration of VCC times integration of VCC dt, 1 over L, integration of VCC dt is equal to 1 over L VCC times T, let's say from 0 to T1, for example, 0 to T, in this case. So it's VCC over L times T, right? So it's a ramp here, assuming initial condition is 0. Okay, let's assume initial condition is 0. So it's a ramp right now, starting from 0 and going to some point here. That point here is equal to VCC divided by L times the value of T1 in this case, right? Okay. How about now during the discharge? We said that we're going to discharge through what? This circuit, right? When the switch is off, we said the inductor current will not change polarity, right? Because inductor current cannot change polarity instantaneously. So this is inductor current, right? IL of T, right? So it was ramping up here using a straight line, right? A ramp, basically, ramp function. And then now I disconnected the switch, disconnected my supply. I have energy stored in the inductor. From 214, what is the current going to look like here? What's I of T going to look like? Two fourteen. Remember, this is an RL circuit, so you would have to, and there's no DC. They don't have a DC source. So it's not a DC circuit. So this is a circuit where you remember the T equals 0 conditions that you were talking about in 214. You have a circuit, and I close the switch at T equals 0. The inductor had a certain current through it. This is the initial condition, and you were solving the circuit, right? So the solution to this was a first order differential equation. We will go through that in more detail, but for now, the solution to this, if you remember, this was an RL circuit. The solution to the current I of T was equal to AE minus T over tau, A to the exponential E to the minus T over tau, where tau is equal to L over R. Remember that? Very long time ago, 214. So anyway, you will do a lot of that, and then all these equations are in your equation sheet, so don't worry about it. And again, in this course, I don't go beyond the first order differential equation, right? So it's either going to be an RL circuit or an RC circuit, right? So that's why it's not a differential equation course. The solution to any first order system is AE to the minus T over tau. A is determined from initial conditions, right? So the idea is not to quiz you on differential equations, because it's something you studied before. But you need to understand that now I have a resistor in my circuit, in my circuit, not just an inductance. When it was an inductance, it was a pure straight ramp. When I'm discharging my inductor energy, exactly, it's exponential. You're going to be discharging through an exponential. That's all I wanted to say, basically. So this is the equation for this AE to the minus T over tau, and you will solve a lot of circuits and problems and learn how to use this. But basically, this is what I wanted to demonstrate. So from T1 now to T2, for example, you're discharging through this exponential waveform. Okay? So what they're asking for here is, so this is this waveform that we talked about. Here they're asking for, the source power. The source is a DC source, right? I have a DC source here. They're asking for the source power. So first, for you to draw the source, to derive the equation to the value of source power, or average power in this case, you have to draw the source voltage and current. The source is a DC source. Voltage is no problem. How about source current? Source current is only current is only drawn from the source from 0 to T1. Do we all agree? Because after T1 here, I have disconnected this switch, so no current is coming from my source anymore. Remember, current is initially coming from the source through the inductor, going back. And then when you open the switch, current in the inductor will dissipate through the resistor. So there's no source current from T1 to T2, for example. It's only from 0 to T1 that there is source current. So I have power from the source is equal to V average voltage from the source times average current from the source. Average voltage from the source, again, it's a DC source, so I can take that out, right? And then I have to integrate the current, because the current is not, a fixed value, it's this ramp, right? And we derived the equation for the current here. So we derived the equation for the current. It's VCC times T over L. That was the equation for the ramp. It's VCC times T over L. Right? So we had derived that previously. And then from T1 to the end of the period, T1 to the end of the period, there is no source current being drawn from the source. Right? So you did the integration from 0 to T, and this was the solution. Right? Okay? That's something we do. Where do you see this circuit being used? Has anybody played with electronics?
What kind?
No, commonly, I think this is, if you played with anything you want, if you tried to switch any lights or did something where you tried to, I don't know, run a motor, for example, with a small microprocessor. Have you done anything like that, out of love for electronics? You have not? I used to have, like a room. I bought an old scope, and I had electronics in my house and everything. I do all the experiments that we used to do in the labs. I used to do at home. I seriously, and I loved it. I thought, people thought I was
My
crazy.
parents give me that when I take things apart.
No, I had the whole apartment for myself. Like my parents' apartment was on the right, mine was on the left, and I had, my friends would come and we would play with electronics. I know, very nerdy, I understand. Very nerdy. But I used to love electronics. So anyway, what? No, I still love electronics. I still love electronics. But one good circuit, one circuit where you really need something like that is where, if you have a relay. The relays are, you can buy them. I mean, the word relay is a very amazing term, because some electronics people use it. It's like a small, box that you would buy, and it's basically a mechanical electromagnetic switch where you have a mechanical contact run by an electromagnet. So you have an electromagnet that pulls the contact or opens it up, and it's basically an inductor that you charge to create some magnetic field to pull or push a contact, right? And you use that all the time. Like, for example, if you want to turn on lights for the first time in your life with a microprocessor, right? You want to impress your parents. I'm sitting here and turning off the lights. You would basically put a relay in series with the light circuit. So you would put a relay, and this relay, for example, would be a box like this. Just a simple box like that, and it would typically have an input would be sort of an electromagnet, and this electromagnet is actually driving a mechanical switch here. And this would be your light bulb, for example, blah, blah, blah. And then you will have your AC source here. Right? So you'll have your AC source in series with your light bulb. So if you close the switch, you're supplying your light bulb from your AC source, right? And these relays will allow you to do that in an isolated fashion. I mean, you cannot connect a computer to your 240 volts, right? You cannot do that. So, but with a relay, you can put a small amplifier circuit here to amplify your current through the coil, and this would be your, microprocessor circuit, for example, your microprocessor be here, right? So your microprocessor will give a, signal to turn on the relay, for example. And then, you'd have an amplifier circuit like you studied in 325 that would take, your 5 volts with no current at all and amplify that, right? Maybe a voltage follower, for example, right? Simple circuit like that. And then this will drive the relay coil, and the relay coil will drive the mechanical contact, right? So it's a very nice simple circuit, and it will impress lots of people very quickly. And this is very commonly used in, motor robots for running motors and turning off motors and flipping their direction, right? If you want to flip a direction of a motor, you want to flip the direction of the source. So you maybe connect the battery through some relays to the load. So you can maybe turn on, and some of these relays have multiple contacts. So one contact will turn off, one contact will turn on, for example, when you energize it. So you can build some intelligent circuits around relays. You can build something like digital circuits around relays. But that way you can control power in a certain way, right? So a relay is a good example because a relay, the input is basically a inductor, and typically you would put around the inductor a circuit like this, because you don't want to open up the relay. Here, I didn't do that. Yeah, so you don't want to open up your relay contacts without having this diode and resistor around it, because then in that case, what's going to happen? Again, this relay has continuous current, right? If you try to, if your amplifier circuit disconnects the current going to the relay without having another alternative path for the current to flow, then you will burn your amplifier circuits, for example, right? So you would typically have a diode and a resistor circuit around any inductor, typically that you've charged and you're going to discharge, charge and discharge, right? Just for freewheeling the inductor energy. That's what it's called. It's called freewheeling the inductor energy, allowing the inductor energy to be dissipated in the resistor. So this is an example of a circuit like that. So people in power electronics did a lot of, there's this freewheeling business helped a lot. The power electronics people developed many different kind of circuits. But then there was a lot of people also working on, they want to optimize power converters to the limit, right? So they want to figure out a way to recover energy. That was, if you have an inductor circuit like that, like a relay that we just wanted to turn on, it's power loss, right? If I'm going to dissipate this energy that I stored in the inductor dissipated into the resistor, I'm losing some power, right? It's not a big amount of power, for example, in a simple relay circuit, but let's say you have a battery-operated device and you want to be able to optimize power consumption as much as possible. What would you do? You would try to, tweak your circuit to be able to recover as much energy as possible. So I know that this energy is being burned. So why not come up with a circuit that intelligently does what I want to do? So has current flowing through the relay, for example, to turn on this switch. At the same time, when I want to turn off the switch, I don't take this energy and dissipate it in a resistor. I recover it and push it back into my power supply, for example, right? You can do that. So a circuit like that would be this, for example. So let's see what happens here. So I have a source here and the same my ground connection here. And but here it's a much more complicated circuit, right? Two switches, 2 diodes. So it's a much more complicated circuit. But let's see what it does. So when the switches are on, they switch on together. When the switches are on, I have current flowing through from my source to ground. So it's a closed loop. I've actually I've actually charged my inductor with energy from the source, right? And then what do I do? What happens later? When you turn off these switches, let's see what the circuit looks like. When you turn off these switches, this is what the circuit now looks like, right? If I turn off these switches, I have current flowing through this inductor. Is it going to swap polarity? It will not. Current in the inductor will only, if I don't have a source across the inductor and it was charged, and now I don't have a source across it, a positive voltage source, then what's going to happen to inductor? The inductor current will discharge, right? So what's going to happen here? Inductor current has to find a place to go, right? So where will it go? I put these diodes around it. So let's look at this. So current will flow from the inductor. Current will not change polarity, right? It can go through this diode. It will forward bias this diode because I'm pushing forward current through the diode. So this can turn on. and wow, it's connected to the source. That's fine. But for me to push current back into the source, I have to have a closed loop, right? So I've added this diode as well. So what will happen? Current will flow out of the inductor, forward bias this diode through the source, and now I flip the polarity of current through the source. What does that mean I'm doing to the source? I'm charging it, right? So that's the passive sign notation we talked about was always assuming that sources have a positive voltage and current is coming out of the positive terminal. If I flip the current polarity, that I'm charging the source, right? So, but I have to have a closed loop. So the closed loop is created by this diode, right? The diode is connected to the negative terminal of the source. So it's going through the positive terminal of the source, back through the negative terminal of the source, through this diode and the inductor. Right? So I did not flip the current to the inductor. I'm discharging the inductor now through the source. What happens when you put a negative voltage across an inductor? So we put a positive voltage. Initially, we had a positive voltage across the inductor, right? It was VCC. And the current looked like a ramp up. This was the inductor current, and this was inductor voltage, right? How about now, what did I do? What I did here was initially the inductor was, this terminal of the inductor was connected to the positive source. This terminal of the inductor was connected to the negative source. Now when the switches are off, this terminal is no longer connected to the positive source. It's connected to the negative source potential. And this point is connected to the positive source potential. So I flipped the polarity of the voltage across the inductor. So what happens when you flip the polarity of voltage across an inductor? Now it's instead of VCC I have, minus VCC. I didn't draw it nicely here. What happens if I put minus VCC across the inductor? What happens to the current? Minus VCC. So with VCC, again, IL is equal to 1 over L integral of V dt, VL dt, plus I0, fine, plus the initial condition. So when I had VCC, positive voltage here, the current was equal to VCC times T over L. How about if I put a negative VCC? What is the current equal to? Negative VCC times T over L. Exactly the same. Plus initial conditions. Plus initial conditions meaning that I will start from here. So I start from my initial condition and then I go with a negative slope. So it's exactly the same slope but negative. It's exactly the same slope because it's the same voltage across the inductor but negative slope. So now instead of discharging through the resistor and burning that power, wow, clever circuit, I can charge my source back again. So this is very nice for applications where you are battery operated, right? But it's more cost, right? I have much more electronics, right? It's a lot more electronics than this simple circuit. And I'm doing the same job, running motors, for example, right? Running a relay, right? So, but in this case, for example, it's a mobile application that requires, longer battery life, and I'm willing to go with, extra complicated circuitry for that purpose.
So when both the diodes are closed, it will be a complete circuit for the source, VCC, right?
Sure.
What if the voltage VCC is more than the voltage across the inductor? Will the current actually pass through?
What if the voltage across the inductor? But the voltage across the inductor is VCC.
So how is current passing through? It's already a complete circuit for the big source, right? The ideal source VCC.
But you have current. I mean, you force current to the circuit. Inductors will force current to flow through a circuit. The inductors will force the diode to turn on.
Okay.
Right? The inductors will force the current to flow. It's like this current source converter I was telling you about. So a current source and it will cause the voltage to be higher, and definitely on one side for sure. Yeah. But you're not controlling the voltage in this case, right? Like the current source converters that we were talking. I mean, I briefly mentioned the current source converter, for example. One of the benefits of the current source converter is that maybe you can use a lower DC voltage to pump current into a higher DC voltage because you're controlling current. So I can use a battery. I can take a battery, and out of that battery put a power converter after that that creates current, and that current I put a big hefty inductor in its path. It will maintain that current constant. It will maintain that current, and it will try to push it to the load. Right. So while doing that, yes, it will create voltages that are higher. So Mu'in is an expert in current source converters, right? Correct me if I'm wrong, yeah. So it will, that's physically what's going to happen, but you're not in control of the voltage, yeah. And again, remember in this case, I don't have any impedances. It would be nice if you go and simulate this and put some impedances in the path, because then you will see the voltages doing some work, yeah. But in this case, if the voltages are exactly equal, if the voltages are equal and the inductor has current, if the voltage across the inductor was equal, remember your 214 circuits? If you have current flowing in there, this was your initial condition, it will flow until it dissipates. Right, so but it would be nice to simulate it. Maybe simulate it with PSpice, and put some resistors in the path so you can look at the voltage. That would be interesting. And maybe send me the results, or let's show them to class next time. Yeah. So here then we show the waveforms here. So obviously we talked about the fact that the slopes are equal, right? This is VCC over L times T. This is VCC over L times T, right? And this is, since the slopes are equal, then this will be double the period as T1, right? Since when we go to the same value of current. Remember, we're always going to be going periodic waveforms. So the periodic waveforms will always have the same peak value of current, same initial starting value, same ending value of current. For steady state periodic waveforms, yeah. So if this is T1, this will be 2T1. And then they go through the same thing, for example, but they ask for power from the source. Yeah, what is power from the source in this case? What is source average power? They don't do it here, but they do this by PSpice, example 2.3, so you can verify, you can look at the PSpice solution to it. But what is average source power in this case? Zero, right? And this is source current, and source voltage is DC, right? So it's just this current multiplied by some value. So because these two times are exactly the same, because the slopes are exactly the same, then the area here is equal to the area here, and average source power in this case is zero, right? So I was able to, again, this is ideal, right? This is not real. Every real circuit will have some resistance, right? So you will have reduced the average source power considerably with a circuit like this, but not eliminated it, of course. Yeah. So this will last a lot longer if you are able to, of course, drive these devices with the same amount of power that you were driving the previous single device, right? So in the previous circuit, you have one power device and one diode. Here you have two power devices and two diodes. So these have losses. So you will have to do a detailed power budget, but if you assume they are ideal switches, then this circuit wins from a power supply, average power perspective. Yeah. But then you have to go into details. So in power electronics, that you go several stages. Right? You first come up with the circuit, figure out how it works, how to control it, etc., etc., and then okay, this is its efficiency. Can I do better? Can I optimize the efficiency? But then to do the efficiency optimization or calculations, you have to consider the power losses across the device. So again, RMS value, again, by definition, RMS is equal to the voltage that will create average or transfer average power to a resistor. So in DC applications, average power across a resistor is equal to what? V squared over R, right? So they're saying that RMS voltage is this effective voltage that is able to produce or power through a resistor equivalently to a DC voltage. So if we're able to come up with this equation, then this V effective is going to be the definition of RMS. So just bear with me. So I mean, it's a definition. Right? So they go through the calculation of average power through a resistor. So this is integration of the instantaneous power, which is an integration of the voltage multiplied by the current, and or the voltage squared instantaneously divided by the resistor, and then they take the resistance out, and they end up with this term. This term is what? This term is the average value of this v squared waveform, right? It's 1 over the period times integration of the period over some waveform, right? So they say that this v effective squared is basically what's in this, between these brackets, yeah. And then this v effective is what's equivalent to this DC voltage producing power through a resistor. All that is nice, definitions, etc., etc. We know that this RMS value is basically one quantity of an AC waveform, or an alternating current waveform that we would like to extract, and it's an indication of the energy that's being transferred to a resistor, or being transferred from one point to the next in the system. Yeah. So they take so basically V effective squared is whatever's in this bracket. They rewrite it here, and they say that V effective is this VRMS because this V effective was able to produce the same amount of power through a resistor in DC. RMS value of any waveform in general is equal to what? Of any sinusoidal waveform. So V RMS is equal to what? So you take a waveform and you square it, right? You first square it, and then you find its mean value. So mean value meaning average value. So it's 1 over the period integration of the same waveform over the period, and then you put it under the square root, right? So it's you square the waveform, you get its mean value, and then put it under the square root, right? So that's RMS value of a waveform. And this is true, of course, for any waveform, whether it's sinusoidal or not. Okay, but what is the RMS value of a sinusoidal waveform with peak value of Vmax? That's something you should know at the top of your head. If you have a sinusoidal waveform that has a peak value of Vmax, Vm, what is its RMS value? You can go through and do this. Fine, you can put sine. What is the equation for this? Vmax sine, for example, omega t dt, and then you square it, for example, and you find the average, and then you put everything under the square root. You can do all of that. But what is it for a sinusoidal waveform? What's the RMS value of a sinusoidal waveform? It's a number that you should have at the top of your head. Yeah, root 2 what? You multiply by root 2? Divide by root 2. So it's the RMS value of a sinusoidal waveform is Vmax over root 2. If you go through this, you will get the same, Vmax over square root of 2. And they prove it here. On the next, not later. So this is, but for a non-RMS value, for a non-sinusoidal waveform, it's not. Okay, so don't assume that the RMS value of any waveform is Vmax over square root of 2, right? It's only for sinusoidal waveforms, right? So only sinusoidal waveforms, the RMS value is Vmax over square root of 2. So they do this, they calculate RMS value for this square waveform, for example. For this square waveform, the RMS values happens to be Vmax times square root of d. And this happens to be the RMS value for any square waveform with a peak value of Vm that is periodic and has a duty ratio of d, the turn-on duty ratio of d. So this will be a useful equation as well. So you will see waveforms of pulse square waves, for example, and you will, okay, what's the RMS value, for example, and you will, it's an equation, or you can go through, of course, the integration, right? You go through the integration by squaring the waveform, finding its average value, putting everything under the square root, and then they go through the integration for you here. Okay? But it's something like the Vmax over square root of 2 thing for the sine wave. For something that you are not very familiar with, let's see how we come up with it. Yeah. So for a sine wave, we said it's Vmax over square root of 2, right? So what if and what is this waveform? So I took my sine wave. This was my sine wave. And for you to calculate the RMS value, we said we will square the waveform, right? So RMS We will first square the waveform. So v of t, I will square it. So v of t squared is what? Will look something like, right? I take this waveform and I square it, right? So it will look something like this. And then I find its average value, right? So does this have an average value or not? This red waveform? It will have an average. It's all above the zero value in zero y-axis line. So it will have a lot. I mean, this whole thing will have a huge average value. But is it a pure DC waveform? It's not a pure DC waveform. Like as long as it's not pure DC, then it will have an average value as well as an AC component, right? So it will have some average value, maybe up here. Okay. How about if and then its RMS value is equal to V max over square root of 2, because this is a sine wave, right? How about if I give you this waveform, just this waveform. So this. So I removed the negative half cycle. So here, what did I do? I found the average value of this new waveform, which is v squared of t, which is the average value is basically the integration of the waveform square divided by a period. What's integration? Integration is the area under the curve. Correct? So now what did I do? If I square this, what do I get? If I square this waveform, same thing, I get this, and then 0, and then this, right? So what happened to my area under the squared signal? What? It's half. It's halved, right? I cut it in half, right? This was during this period, during my switching period, t, during my full cycle period. Here I had, this big area under the curve. Now during this big period, during my period, I had half the area basically, right? So this integration of v squared now is half the area, right? So I want the whole I'm trying to get you to come up with the RMS value for this new waveform without going through the equations, right? So how would you do that? So we know that for the sine wave, it's V max over square root of 2. For this new waveform, which is a half wave rectified sine wave is what we call it, I know that the area was divided by 2. All of that is going under the square root. The rest is the same because the equation for this curve is the same as the equation for this curve from 0 to t over 2. From 0 to t over 2, the equation is the same, right? So I can sort of say that the RMS value for this new waveform is V max. Instead of divided by square root of 2, I have another what? I have another half under my square root. Is this fair? Because if this area, so if this is the integration, I divide my integration. Integration is the area under the curve. I took that, I divided by half. And then, of course, I divided by my period as well. It doesn't change. So it's like V max over square root of 2 divided by square root of 2 or V max over 2. Okay? So how about something like, so this is what we were just talking about. Okay, so how about something like this, more complicated, okay? So I have a waveform. This is a typical waveform that we will see in power electronics, the current waveform, for example. Like this current waveform, this pulse current waveform is something that we typically see in power electronics. We will talk about that in the next chapter. But it's a waveform. And then on the phases A and B and C, you will see the same waveform, A, B, and C. This is phase A, phase B, and C. I'm just telling you now that this is what this current looks like. You can take it for granted for now, and then we'll figure out later where this shape comes from. And then what happens at this node here? Current through here goes back to the same node. Current through here goes back to the same node. Current through here goes back to the same node. Right? So all the currents add up, right? The Kirchhoff current law. The sum of currents at this node is equal to 0. That means IA plus IB plus IC is equal to this IN current, right? So IA plus IB plus IC is equal to this IN current. So if IA has an RMS value of IRMS, right? IRMS is the IA current, right? What's the RMS value of this neutral current? So IA has a RMS value of, this has I RMS is equal to I X RMS. And now I'm telling you that this neutral current has 3 times these pulses in the same period. I'm not gonna, 3 times the pulses. It has from IA, it has ones from IB, it has pulses from IC as well. So 3 times the number of pulses. So what's the RMS value of this new waveform? Is it times 3 or times square root of 3, right? Because it's the area under the square root, right? It's area under the square root. So square root of 3 times Ix RMS is the RMS value for this new waveform, right? So what this also tells you that if you want to find the RMS value of any waveform, you can chop it up into smaller waveforms and add them up in a certain fashion under the square root, or square them and add them, as you will see later, and you will be able to calculate the RMS value. This will be helpful in cases where certain waveforms for example, you were given a waveform that's, for example, the triangular waveform has a certain RMS. For example, you calculated it before. And now I'm telling you what's the RMS value of this waveform. You can go through the cycle of coming up with the equation of this line, integrating from 0 to T1, from T1 to T, etc., etc. Or you can think of this as what? You can think of this as this triangular waveform with for example, this has a 5 amp peak-to-peak value and a DC offset, right? What's the RMS value of a DC value? The same. That's the DC value, right? So you know the RMS value of this waveform, and you already know the RMS value of this waveform. Instead of having to go through and finding the RMS value, the equation of this line, doing the integrations, etc., etc., right? It would be much more complicated in this case, assuming you have the RMS value for this. And something like that, you maybe have the RMS value because I will give you, for example, I will give you a Fourier series, or I have it somewhere. Fourier series of common waveforms. So you'll be given common waveforms, and you will be given. I would not expect. We will do a lot of Fourier series. As you know, we are going to be concerned with waveforms that are sinusoidal as well as non-sinusoidal. Non-sinusoidal waveforms, we said they will have a DC component, which is our average value, and then an AC component. To understand this AC component and design filters for it, etc., etc., I need to understand, the harmonic content or the frequency content of that waveform. How do you do that? What's the mathematical tool? Fourier series, right? That's a mathematical tool that you've learned about to use to do this kind of work. This is not a course on math, so it's not a course in differential equations, it's not a course in Fourier series, so I don't expect you to derive the Fourier series of complex functions. I will give you some Fourier series of specific functions that are commonly used in power electronics. And then from the Fourier series, we should be able to calculate the RMS values, peak values, average values, etc., etc. You'll be able to utilize those tools here. So we stop here for now. So I think RMS value calculation. The next thing we'll do is continue talking about power calculations as well. So we'll stop here and continue next time. Again, this chapter, I apologize, it's a simple review, but